So this is part 2 of lesson 2.3. Now we're going to be talking about this thing called an equilibrium. All right, that's a brand new word for us. Most of us probably have never heard that word. However, it does have a base word that we might be familiar with, equal, right? So that just means equal or same size, okay? So we've been talking about the resultant, right? And we've never added this thing called an equilibrium in. All right, so for example, the equilibrium is the force that is equal in magnitude and opposite the direction of the resultant force. Okay, so whatever direction the resultant is pointing in, we're going to have the same magnitude, so the same length arrow, a part of that diagram now. However, it's going to point in the opposite direction, and that is going to represent the equilibrium. So if I were to add that in now, because I am the same magnitude and pointing in the opposite directions, if we're talking about the whole system and we know that a net force is the sum of all forces, however, we know that when things are at rest or in constant velocity, we know the forces cancel out. And they cancel out because the magnitudes are the same, but the forces are pointing in the opposite directions. So that means when we add in an equilibrium into our system now, due to the fact that it is the same magnitude as the resultant, but it's pointing in the opposite direction, the net force of the whole system now becomes 0 newtons, all right? This first part right here, where it says equal in magnitude, opposite direction, that should remind you of the third law from when we were talking about Newton's 3 laws. All right, so for example, you have this diagram. So you have 12 newtons pointing up and 19 newtons pointing towards the right. They do draw in a resultant, and they go from the tip of the first vector to the they go from the tail of the first vector to the tip of the last vector, and we do see a triangle here. But now that we have to add in an equilibrium, what ends up happening is this. An equilibrium is going to be drawn from where this, where this dot is right here, and it gets extended out the same amount of length, and you just label it equilibrium. Okay, so because we see that they are the same size, we know that they cancel each other out in a system, and they make the net force 0. Okay, so let's do a practice run. So we're going to solve for the resultant using the information given on the diagram, and then we're going to draw in the resultant and the equilibrium vectors. Okay, so think of when we're solving for a resultant with forces, think of like we're literally looking for a net force. Okay, so we know that the net force F net equals the sum of all forces. Okay, so again, just like the number line I'm always going to be using, we have positive going towards the right, negatives going towards the left. F net equals 27 newtons plus negative 12 newtons. Okay, F net equals 15 newtons. Just plug it into your calculator. There's no reason why we have to do any sort of math in our heads. You are more than welcome to use a calculator. So now that we know it's 15 newtons, given that it is positive, we are clearly going to have to point it towards the right, right? Because the resultant follows whatever the direction. If it's negative, we would have pointed to the left side. If it's positive, we point to the right side. So we take this and we start from this little dot. We draw it out. 15 newtons. Okay, so actually I'm gonna, just so that I could emphasize it just a little bit, I'm gonna draw it out just a little bit longer. Okay, so the idea here is that this vector right here is larger than this 12 newton force vector. Okay, let's draw in our equilibrium now. So I'm going to draw the equilibrium in this bright blue. So again, I'm going to go out like this. So now I have an equilibrium equals 15 newtons. As you can see, they are the same length. They are just pointing in the opposite directions.